will not mention is PhD with quite a lot of that was on superconductivity, and he collaborated with me also on these carbon disulfide measurements, and was extremely good student, actually, one of my best experiences. So education in its bachelor was to go from University of Colombo, Sri Lanka, and PhD, that was, as I mentioned, from next step in his career was Ike's lab, and that's mostly about this stuff.
Right. Okay. Thank you very much for the introduction, and thank you very much for inviting me to give this talk. So the apparatus you're seeing is the diamond anvil cell, from everyone in this audience knows. And the one thing that I want to point out, I think this picture is taken in this lab, but I'm not sure. So I found it from the internet. I just used it. So to get some credit, give some credit, I can find different sources, but my best guess is probably taken from a geophysical lab. All right. So before I start my talk, I would like to acknowledge these individuals who helped me throughout my research at Harvard. Advisor Isaac Silvera and the present and the past group members, and some of the scientific discussion from Edinburgh group, and one person here from happened to be my colleague, and for the CNS and Matthew Turner from the Walsworth group, who help us with the diamond preparation and the funding. Okay, so I'll give you a little bit of a very brief introduction about high pressure science and what we can do, and then I'll get into hydrogen stuff. All right, so since we're talking about pressure, I have to get some units. So the main unit we use is the gigapascal, which is roughly equal to 10,000 atmosphere or 10,000 bar. And the another calibration we can use is the pressure of the center of Earth, which happen to be 3.6 million atmosphere or 360 GPa. So to get understanding what's really going to happen when you apply from 1 atm to 360 GPa, so what could happen to a material? So the basic thing you can think of is a huge reduction of volume. So solid hydrogen, for example, it reduces at least 14-fold, and hard metal like iron 2 times, water 3 times, and alkali metal at least around order of 5. And another interesting example is the diamond. The graphite is the most stable form, but if you squeeze it with higher pressure and higher temperature, you can make diamond, and they're stable material. So the density is one of the reasons that we have this stable diamond samples. And how do you generate really high pressures? We use the apparatus called diamond anvil cell, and you have 2 diamonds sitting opposite each other, and you have a sample chamber, and you apply force. And how big is this? Depending on the how high pressure you want to go. Smaller the area, higher the pressure you can get. And there's another way of getting high pressures using the dynamic compression. These are static. Also, you can go to the really dynamic high pressures by using the dynamic compression. This is a picture of a Washington State University gas guns. So here we are talking about the very small time scale. And in this way, you go to really high pressures, but same time you go up in temperature too. All right, so what really happened is, I'll give you one example. This is a Boston subway, and this is a subway compartment, and I'm going to use this as the fixed volume, and I'm adding people, which represent the number of atoms. So you go in from rush hour, so you get more people, right? So get more nearest neighbors. You increase your coordination number. And then if you keep going, it's rush hour, so you get really packed here, right? So this is the day that they call the no pants day at Boston. So if you look at here, they ride without pants. So this kind of will give you an analogy of when you squeeze material to really high pressures, at some point, electron going to rip apart and get delocalized. So this symbolizes what's that happening. So in actual case, what happened is, in our case, the volume is changing, the number of particles is fixed. So, but you can think of this as the exact same thing, right? So this is kind of like a rule. So you have constant number of particles, and you're squeezing, you're densing, you're increasing the coordination. But unless you go to India, you get different things. You increase in the volume, which is unusual. All right. So I'll give you 3 very nice, famous examples of what could happen under pressure. So one of the very famous example is carbon dioxide. This SiO2, we all know, is quartz, and we have 4-folded SiO2 structure. But carbon dioxide, on the other hand, it's a gas at ambient condition, right? And then, but if you squeeze this one a little bit higher pressures, and these are the synthetic conditions, 40 GPa at 1800 Kelvin, you can get four-folded CO2, the extended form of carbon dioxide. You have two coordinate, increasing from coordination number 2 to 4. Even if you go higher up in pressure, it goes six-folded. So oxygen has this very nice scarlet red oxygen and become these O8 molecules, and it superconduct at 100 GPa and metallized too, metallized and superconductivity. And on the other hand, another one example is the nitrogen. Nitrogen, the triple bonded, one of the strongest bonded, but at this synthetic condition, it goes to a single bonded nitrogen. So increasing the coordination, you give up this energy to go to this form of nitrogen. So once you release this one, you can get enormous amounts of energy, so high energy density materials. These are one of the very famous examples. So what really happened is when you squeeze the material, at the beginning, you're really squeezing at the attractive part of the potential, you're really squeezing the van der Waals space. So then when you penetrate to the repulsive region, which you're going to get this, the electron going to rip apart and then get delocalized, give all sort of new electronic properties. So pressure is derivative of energy versus volume, and you actually what you're doing is you're really tuning the energy landscape of a material. So you can mold material, you can twin material to make new materials. All right, so if you look at this one, this is the part that at least is interest most to me. So if you take an insulator, so you have a band gap, right? But at some point when it's Wilson transition, if you increase the pressure, at some point it's valence band and the conduction band, they're going to interact and then have band overlap, and you can have insulator metal transition. So xenon, one of the famous examples, it's a noble gas. Who would think that could be a metal? If you squeeze to 130 GPa, xenon go to insulator metal transition, and it's a transparent metal. It's metal with very small plasma frequencies, 0.426 electron volts. And oxygen become insulator metal transition, go to insulator metal transition, and iodine, cesium iodide, there are various kind of examples. And also oxygen, one of the molecular system, it goes to superconducting transition. And so in this way, you can think that take any material and squeeze it, you can make a metal out of it, right? So, but it's not the case. So there are some other examples too. But if you take alkali metals, if you squeeze them, it goes back. It goes to insulator. So there are some things that we really don't understand. So it's very interesting to study and understand how the electronic nature of a material change when you apply pressure. All right. So another one of the famous examples is pressure-induced superconductivity. So at this graph, you can see here and the superconducting transition temperature. The highest TC known was 164 under pressure on cuprates. But then recently we found the H2S superconductor at 203 Kelvin. So highest known TC so far under pressure. So this kind of sparked the interest of studying new material, new superconducting material. So this gives a foundation to really study on hydrogen, because hydrogen predicted to be a high TC superconductor, which has a lot of various other properties which I'm going to talk about. So outline of my talk going to be the first part. I'll show you a new low temperature phase transition on hydrogen. And the second part of my talk, I'll show you the Wigner-Hunting transition to metallic hydrogen. And the last part of my talk, I'll discuss some of the work on hydrogen deuterium. Like you have a hydrogen, and if you remove one hydrogen and add deuterium, you have HD. So how HD behave under pressure, pure HD. Not about mixing H2 and D2 and making HD, just squeezing pure HD. All right, so hydrogen. So it's been predicted a long time ago, more than 88 years ago, or at 1935, Wigner and Hunter, they predict that if you apply sufficient pressure, a hydrogen can go to insulator metal transition. So it's to start with the molecular solid, it's insulator, and then at some point it can be molecular metal, and if you squeeze hard enough, it can be atomic metal. So the density, we're talking about one here and somewhere around 14 order. And the pressure, the calculated pressure so far, the predicted pressure is around 400 to 600 GPa to have this transition. And hydrogen, we all know, is a quantum solid, so it's a very important system to study. So it has a very high de Broglie parameter. Because of that, it introduced huge anharmonicity to the system. So which give rise to different kind of properties. It's predicted to be a room temperature superconductor, and it's also predicted to be a superfluid. And some people predicted that could be a superconducting superfluid. All the superfluid we know they are insulated. Right? So what if you have a metallic superfluid or superconducting superfluid? And also it's a highly energetic material. These all are predictions. And the zero temperature quantum liquid has a very high 0 point energy. We're talking about 3,000 Kelvin. And in terms of in terms of planetary science, it's very important to understand how inside the giant planets, how this material behaves. Like it's a liquid molten metal, give rise to this dynamo effect or high magnetic field, all sort of things. So fundamentally, and in terms of application, also it's very important material to study. All right, so this graph shows you year and the prediction of pressure for solid metallic hydrogen. Blue dots are the experiment, red dots are the predictions. So if you look at this one, start here, 25 GPa, but right now you are in somewhere around 400 to 600 GPa. So every time when theories predict one pressure and experimentally get there, nothing happened, theory changed, it kept going up, and it landed somewhere here. But there are some of the metallic hydrogen publications claiming a liquid metallic hydrogen in 1996, first by Bill Nellis at Livermore Lab, and they predicted, they observed the liquid metallic hydrogen, and also this is under dynamic conditions. And in our lab last year, we published one paper on static condition for liquid hydrogen. And also a year before, there's some work from Sandia National Lab for liquid metallic deuterium. So the liquid hydrogen has been there for a while. So the solid, the Wigner-Huntington transition is the one, that challenging one, has not been observed experimentally. All right, so these are high temperature ones. These experiments are. So my interest is going to really low temperature and study the solid state of hydrogen. So start with, you have this strongly bonded dynamic gas, which has a para and ortho species. You cool it down, first liquefied to 20.3 Kelvin, but James do, and then you have a molecular liquid, doesn't have permanent dipole moment, and it first solidified in 1899, 14 Kelvin, and you have this J is equal to 0, the para state, the freely rotating quantum rotors. So my interest is getting to here and then go squeeze this material to really higher pressures at low temperatures. So I'll show you the phase diagram at low temperature, below the room temperature region. So this is the known phase diagram so far. So at low pressures, you have phase 1, and then you have a broken symmetry phase, around 110 GPa, and then you have this A phase, the phase 3, and the recently discovered phase 4, which is a graphene-like phase. And here were the predictions for the solid metallic hydrogen. The phase 1, as I'm saying, is a freely rotating molecule, HP structure, and you have a broken symmetry phase. When you squeeze molecule to high and high pressure, the interaction is going to increase, and the J is not going to be a good quantum number anymore. So it's the broken symmetry. Your symmetry is going to break, and you have this rise to this new phase. And here you have this induced. Hydrogen doesn't have a permanent dipole moment, right? But here you get very strong IR activity because of the induced dipole moment. And you have this phase 4, the graphene-like phase. And none of these phases were observed to be metallic. It's transparent, at least up to 360 GPa. All right, so before I show you my results, I'll give you, hydrogen is how you really detect a phase transition in hydrogen. How do you know these phases, how they detect these phase transition? So doing X-ray is the best way to do a phase transition, but doing it for hydrogen is a very difficult system. But material like hydrogen, what you can do is you can use a spectroscopic techniques to detect phase transition. In the vicinity of a phase transition, you can see appearing and disappearing of those vibrational modes. So if you look at this figure, here you have a pressure versus frequency. This is a deuterium vibron. You can see at some point all this disappeared, and there's a new peak appear right here. So indicating there's some symmetry change you have going in a phase transition. So this is how we detect a phase transition in a material like hydrogen. So you have this phonon ranging from 40 to 1,000 inverse centimeters, and then you have rotones, and you have vibron above 4,000 inverse centimeters. So by tracking the vibron or the other modes, phonons or rotation, you can really detect the phase transition in material like hydrogen. All right, so this is our experimental setup. So we have Raman and IR setup. We can do it simultaneously, and we can do a 4-probe technique to measure the conductivity and magnetic susceptibility measurements, and its diamond is transparent, so you do all sort of spectroscopic techniques. All right, so one of the big thing happened in recent studies in our lab is we were able to consistently go into a really high pressure, pushing the pressure more than 400 GPa. So what we did different, I'll give you a few steps, few examples of what we did different to get to that pressures. So in terms of hydrogen, it's a very nasty material, it's very reactive, and it can go into the diamond and crack the diamond, and diffusion is a big problem. And if you shine the laser, they trigger those defects and break the diamond. So there's some surface defects, even though if you take the polished diamond, you have a lot of surface defects. So we will develop a technique, got to come up with a recipe for reactive ion etching to remove those defects. So what you're seeing in this picture is, when you look at through the AFM, you can see, even though they're polished diamond, you can see some defects. So we've been able to remove those surface defects and even the subsurface defects to create any diffusion or any cracks. And also we anneal the diamond to reduce the internal stress, and to prevent the diffusion, hydrogen going into the diamond, we put a diffusion barrier. We use Al2O3 aluminum oxide, 50 nanometer thick alumina layer on top of that whole diamond to prevent the diffusion. And also we were using very low laser power, not to give any laser shock to break the diamond. So, and then obviously they refined the diamond analysis cell and all those things. So all these things all together, the package worked well for us to go to really higher pressures consistently. All right, so I'll show you some results for mainly on IR. So we were mainly doing IR spectroscopy because we don't want to shine too much laser, chance of breaking the diamond. We only use the laser to measure the pressure, get the diamond line. So what you're seeing, right, this is a raw spectrum of hydrogen vibron. So I'm only going to show you from around above 150 GPa, because below 150 GPa, it's very weak. You're almost not going to see any, at low pressure phase, you don't have a, yes? There's a question? Oh, sorry. No. All right. What you're seeing here is a raw spectrum, the power spectrum coming from the interferometer. If you look at here, right here, 150 GPa, you can see there's something happening. There was nothing here, and then you have some absorption right here and right here, which is the characteristic feature for phase 3 vibron. Right? If you go up in pressure at around 340 GPa, does it disappear? And there's more new absorption peak appear, the broad peak appears somewhere here, and go up in pressure. So above 380, it gets really dark, and by 400 GPa, it's completely dark. You can't get any signal out. So this is 400 GPa is the maximum you can really go and measure. So this is raw spectrum, you can see, right? But then how you really get how you're really going to get the real peak, real absorption peak? So normalization of IR spectroscopy is one of the big challenges. So in a general term, you can go sample in, sample out technique. Right? You just put a sample, you touch the sample, you measure the background, and you put the sample, and then you get the intensity profile, and then you divide it, and then you can get that one. But in the pressure, under pressure, you can't do that. You can remove the sample and put back to same pressure. So you have to come up with a different way of normalizing, because this is very important. That can give rise to different peaks. So what we did, so if this is what's going to happen in terms of mathematics. If you look at this one here, the transmitted intensity in the absence of sample, I naught, and you have I, which is the transmitted intensity with the sample. And you have alpha, which is the absorption coefficient, and the D is the thickness of the sample. So this is what you have right here. And what you can do is, you can use, so if you want to normalize this one, if you use the empty cell, your D is different, right? The sample thickness is different. You're comparing alpha D1 to alpha D2. So But you can really, if you, let's say you have a phase transition right here, something happening right here, and if you use one of the spectrum lower pressures to normalize this one, that's also a possibility, right? You can do this one, but still, your D is different, the thickness of the sample. So another thing you can do is you have the same pressure, but you go up in temperature, go to a different phase. You keep the alpha D constant and use a different spectrum at higher temperature, different phase, to normalize your spectrum. So those are the best normalization background that you can use to normalize the spectrum in a material like hydrogen. So as I said, empty cell, or you can use a different phase, low pressure phase, or high temperature phase at the same pressure. So I'll show you all these three examples. So there's something happening right here. This is very clear, right? This peak is very clear. You can see that the absorption, which is very enormous increase in intensity. It goes to like 10 to the third power of 10 to the third compared to the other phases. So if you use the empty cell, you have the same thing. But your detail is your transmission. The alpha D you're really comparing is not, you don't have a qualitative understanding how much is the absorption. But if you can use a different low pressure phase, you still have it. But if you use the same thickness but higher temperature, you can get a qualitative understanding what's really the absorption, what is the alpha D, and you can calculate or various other things that you want to. So we were mainly using the high temperature phase, but in here, this is very clear absorption, so you can use the low pressure one or the high temperature empty cell spectrum. So when you normalize it based on those, these are the raw spectrum from normalized from the I. So our I note, I was using this, and for the higher pressure phase transition, and the low pressure one I was using the empty cell, which is very prominent. So here you have the starting of the phase 3, vibron, keep going, raising up, and it get broader and broader, and around here disappeared, and then you have this new broad peak appear around 3200, and it's another big peak right here. So we call this one, if you look at, we call this phase H2 pre, probably meaning that it's the phase before metallization, so pre-metallization pressure. So if you, so the main characteristic, you have two peaks around 2920 and 3300, and there was a small peak. It's very hard to really see this one. Sometimes we do see this one, sometimes it doesn't. So I'm not sure whether this is real, like it's very weak. So here what I'm going to show you is I'm going to show you how it changed when you go up in temperature. So here you go up in pressure and you have the new phase, right? And then at around here, this pressure, you go up in temperature and see how it evolves. So this is raw spectrum again. This is a power spectrum you collected from your interferometer, and then you go up in temperature, 140, 190, 120. So this absorption is, you can see it's disappearing. And if you normalize this, see it goes up. And this is probably phase 4. It's very weak. Phase 4, these conditions are really weak. All right. So, and we were using the diamond line to measure the pressure all the way up to here. These are the diamond spectrum, and this is one of the images. And it get really dark right here, and then get really opaque around 400 GPa. So if I plot pressure versus frequency, this is what the same graph that I was showing you for the D2. So you have phase 3 going up in here, and it's disappear, the two new bands appear right here. And we reproduce this one three times. We saw the exact same broad peak around this region, indicating a new phase transition. Yes?
So what is the high temperature phase you're using as a reference?
It's this one. It's phase. This one. This is probably phase 4. I can only see this broad peak right here, but phase 4 has two peaks, around right here and right here. But these are very at around 360, 370 GPa. Phase 4 is very weak too. So I was using. So in terms of phase diagram, if I go back, so I'm right here. I'm actually mapping the phase line right here. So what we did is one we squeeze at 5 Kelvin, another one we squeeze at 83 Kelvin, and go a little bit higher in pressure, and then we went up in temperature and go to the different phase and went back and squeeze again. So those are the thermal one. So we had 3 points for phase line.
Did you show us the raw spectrum of phase 4?
These are all raw spectrum. All these are raw spectrum. This is raw spectrum. These are raw spectrum. Normalized. So this is the phase 4 right here. No, these are raw spectrum. This is raw spectrum. This is no after you normalize. This is power spectrum you're getting from out of your interferometer. This is after you normalize. This is raw spectrum. This is yeah.
That highest spot is the reference.
Yeah, yeah. This is raw spectrum. All these are all raw spectrum. These are all raw spectrum, and these are normalized. These are two. This is raw spectrum, and this is my reference. When you normalize, you have this. Okay. This is normalized spectrum. This is raw spectrum, and this is normalized spectrum. Okay. Yeah, sure. So here, so you have so new phase transition right here. So to understand what is this new phase, can we get a real, understanding what is this? So I dig into some of the theoretical work. I'm not a theorist, but I try to understand what could be this new phase. So some of the work from the Cambridge group and some of the work from Illinois group. So they have this theoretical phase diagram, which they predicted some new phase transition somewhere around here, 340 GPa. And it goes CMCA 12, phase 3 go to this, and there's another phase transition right here around 430, and then it goes to atomic phase transition around 480. These are the theoretical phase diagram. And this phase has two IR active modes from this prediction. So these are the enthalpy for the CMCA 12 structure. So if you look at right here, around 350 GPa, the CMCA 12 get more stable, and it has two characteristic peaks, 3223 and 3587, around this pressure. And if you look at the difference between these two and the pressure dependence of these two peaks, somewhere around has 360 inverse centimeter, and these are the difference. And here they're showing the stability of their atomic phase, blue one, CMCA 12, CMCA 4, and then atomic. All right. So if I look at my spectrum right here, our data, so we have two peaks around 2980 and 3350. Right? So it's lower than, at least around 300 inverse centimeter lower than what they predicted. But they have this very similar differences in peaks and very similar pressure dependence. So this is the best guess we can get. This is probably something similar to CMCA 12 structure. And these calculations done, so if you add the anharmonic correction, the 0-point energy, probably this will be softened. So what you can say is the best guess is the CMCA 12. This is much more needed, theoretical work will be needed, but from the literature I have right now, it's similar to what we observe is the CMCA 12 structure. All right. So while we were doing this one, so we were tracking how visually the sample change. So to start with, this is one of the picture from around low pressures around 200 GPa. So you have transmitted light coming here, and if you go up in pressure around 400 GPa, there's no any transmitted light coming through, but only the reflected light you can see is going dark, it's getting opaque. And if you go up in pressure around like another 100 GPa, 80 GPa, it gets really reflective. So these are only from the rostrum. These are transmitted. There's no any transmitted light. You see this images through the reflected light. So transmitted light goes to it goes from transparent to opaque to reflective. So visually, this suggests that probably the band gap is closing. Right. So next step, what we thought of doing is, okay, so visually we can see that there's something happening with the band gap. So how are we going to prove this one in optical, using the optical properties, how it could be a metal or not? So we use the simple Drude analysis, Drude model. So by using the Drude model, you can fit to the Drude parameters and calculate all the values you need, plasma frequency or tau, or from that you can deduce the conductivity. So we use the simple Drude analysis to measure the optical properties. So from that you can deduce the omega, and here you have, so here's the reflectance. The ND is the diamond that we know. So what you're seeing right here is the energy versus the reflectance. So we have two different wavelengths we're using from 0.8 to 3.06. So these are 4 different wavelengths and 2 different temperatures, 83 Kelvin and 5 Kelvin. So these are the plaster frequency and the tau deduced from this, and you have reflectance as high as 90%. So there's a problem with the diamond absorption. So we were not sure. In our main paper, there was a calculation error. So we corrected that one by removing these 2 points, in the sense that, so we don't know how the diamond absorption right here. We can't really get the quantitative value, but these are higher. The IR reflectivity is not really affected, so we use those to deduce this transition. From those, you can get the plasma frequency and the tau, and then you can calculate the electron density. It came up with 7.7 times 10 to the 23, and the theoretical estimation is around 6.6 to 8.2. So we are well within the theoretical estimation, roughly. And then from there, we can deduce the conductivity. It's 10 to the 7 order of 10 to the 7 and seems per centimeter. So this is in theoretical point of view, and then all from the optical properties. It says you have atomic metallic hydrogen. So if I compare this one with the other elements, there's a huge difference compared to the other alkali metals, lithium or sodium or potassium. You have 33.2 electron volt plaster frequency compared to other material, and the electron density is also really high. So if I conclude the first part of my talk, so you have, this is the latest phase diagram right now. So you have phase 1, phase 2, phase 3, which is known phases. But not many people, until recently, this phase line was really mapped. Erimets et al., they really mapped this phase line going from 1 to 3 to 1 and 3 to 1. So we have this phase line now, and we have phase 4 phase line done by Jar, and then we have this new phase line. We have 3 points right here and here, right here. And Erimets et al., they also observe something here. So what they're taking is they were squeezing at room temperature all the way up to higher pressures, and they were cooling down. And they saw disappearing of some of the lattice modes. But to compare our work and then their work, there is no any vibron I can compare with. But seems like what we are observing is the same phase, but they're taking the 2 different thermodynamic parts. And here we observe this metallic transition to metallic hydrogen. All right. If I summarize, so we went to a really higher pressures, and we observe a new phase transition somewhere around 360 GPa. And from the Drude analysis, we get electron density of around 7.7, and we produce the dissociative transition to solid metallic hydrogen. So the last part, I'll briefly discuss about the recent work on hydrogen deuterite. So what we did right here, we remove one of the, so we studying pure HD. It's very important to, it's not a mix. We didn't mix H2 or D2 to form HD. We just use a pure HD to squeeze to really high pressures. So these are some of the earlier work. So people only been studied this one to up to 150 GPa. So it has a small dipole moment, and Brown and Daniel, 1992, at lower pressures, they observed this one. If you mix H2 and D2, you can form HD at very low pressures, low as few kilobars, and then they studied this one to really high pressures. Moshari in 1993, they studied pure HD up to 110 GPa at liquid nitrogen temperatures, and they observe HD going to H2 and D2. They did not observe anything happening going in this direction. So people have been observe H2, D2 goes to HD, but not HD goes to H2 or D2. And in 2006, they studied up to 160 GPa. Then they mapped its phase 1, 2, 3 phase line right here, triple point, but they have not observed anything transition going from HD to H2 to D2. So HD was stable up to 160 GPa from early studies. So first, I'll show you the summary of my results, and then I'll show you some of the evidence to support this summary. Okay. So this is what people have been studied: phase 1 to 3, 1 to 2 boundary, and 2 to 3 boundary, and then people also found this triple point. So in our study, we found the triple point again. We confirmed the triple point, and we map the phase 3 to 1 boundary. And around 200 GPa, the very interesting thing we observe is we observe HD it goes dissociated, recombined for H2 to D2. So you can see H2 and D2 appearing in a pure HD molecule. So there's some dissociative and recombination transition happening around 200 GPa. So we map that phase line, and there's new phase transition too. And if you go up in more pressure, there's another new phase transition around 260 GPa on HD. So this now actually right here, it more for like a mixture of HD, H2, and D2. It's stable up to here, but above this pressure, it's behave very differently because of this. It's all mixed compared to pure H2 or D2. All right. So the first one, the H2 to the phase, this one, the transition right here. So what you're seeing the spectrum, this is after you normalize it, we fit the spectrum. So what you're seeing right here, the fitted spectrum. So here you have phase 3, characteristic peak of the phase 3 of HD, and some of the H2 impurity. To start with, we have 4%, roughly around 4% impurity. So if you squeeze around 200 GPa, you can see enhancing in the H2 vibron, and also you can see the D2 appearing. So indicating that HD molecule is going to HD, H2, and D2. And if you go, so I will use this small simulation. It's not done by me, it's done from Ma to explain this dissociation and recombination process. Right here, what you're seeing is the 2 hydrogen molecules. It's all hydrogen, and it's just bigger to see it properly. So at some point, you can see this one is dissociate and recombine. Yeah, he dissociate and then recombine again. Yep. So what probably happening in HD also, you get H2, you get HD, dissociate H2 and D2 and recombine and come to equilibrium. So we study a little bit of equilibrium kinetics, and we roughly, by using the Avirami equations, and we found that roughly it goes to 25% H2, D2, and around 50% HD. All right, and then there's another phase transition, which I told you on HD, which indicating the appearing of a new peak. We have 2 peaks, is split into another new peak. And this one, we go up in temperature. We map the phase line by going up in pressure and the temperature, and to map the phase line. So if I show you the pressure dependence and the frequency right here, you have low pressure phases. And right here, you can see the deuterium appear, and then you have H2, and about 260 GPa, so another new peak appear in HD. It's indicating 2 new phase transition and the dissociation and recombination process right here. Because here only you have pure HD, but right now you have H2 and D2. So here's the spectrum. If you look at here, it's how it transforms. HD goes to H2, D2, and then another new peak appear. It gets broad, go up in pressure. So this is the current phase diagram for HD. So you have now the recombination, dissociation and recombination process right here, and you have this new phase transition, which we map by going up go to a new phase and coming down, go up in pressure, and going up in temperature, just mapping the phase line. All right, if I summarize this, HD undergoes a dissociation and recombination process around 200 GPa, and probably nuclear exchange probably take place in homonuclear species too, but it's difficult to detect. And we observe 2 new phase transition, and this also is very significantly different from the POH2 or D2 material. All right, so to summarize all this work, so in terms of going in the future direction, so we have some indication of metallic hydrogen showing a shiny sample at around 500 GPa. So the next things to line up to is to reproduce this one and to really study this, is it solid? So some people can ask this, how do you know this is really a solid, or if it's a liquid? So we need to study that one to understand, repeat this one and see whether it's a liquid or solid. And also if it is solid, what is it going to be, a superconductor? And if it is superconductor, what temperature will it be? A room temperature superconductor or low temperature? And what type of superconductor? We will follow the BCS model. Should we do the isotopic studies? And if it is liquid, then will be first liquid metal at T equals 0, and there's the liquid superconductors, and all this gives rise to this new quantum state of matter, which is a very interesting fundamental problem to study. And also, will 0 Kelvin liquid, will exist at really higher pressures. We're basically talking about quantum melting, or what's the shape of the melting line? Where it's going to meet the solid phases at higher pressures? Also, it's metastable, or will be highly energetic. So those are a lot of unanswered, rich questions to do in terms of future. So we just scratched the surface of looking at this shiny sample. So there are more exciting works to be come. All right, thank you.
Yeah, thank you, Ranga. And questions?
All right.
Can I keep asking about the reference?
Sure.
So can you show us in the raw data the transitions?
The new phase, right? To the new phase transition?
Yeah, I guess to 3 and then from 3 to 3.
Yeah, right here. This is the raw spectrum. So if here, this is you have almost in the phase 2, 3 vicinity.
That looks,
Yeah. So because it's look clear because it's very intense. Phase 3 is highly IR active. I have a plot. I don't think I have right now. So integrated intensity of IR peak compared to low pressure is like 10 to the 3. Yeah. So if you look at right here, the red one right here, this is. You can use this one as your reference, to be honest. So this is phase. The blue one is 340 GPa. Okay, right here.
the blue one looks like the pink one.
No, this is exactly. Exactly, it's because it's the same phase, right?
Okay.
But here, the red one is 365, which is a different phase. So okay, it goes. Okay, the sample size is really decreased, and we don't have a synchrotron. We use a simple thermal source, so our signal is very weak. So we accumulate like 40 minutes to get the spectrum. So it's very weak. So at higher the pressure goes and goes there, and it's also get really dark and opaque. So you're not going to get very strong signal. So right here, but it's very clear. You can see this absorption in 3 different runs.
Okay. Could you show like that you reproduce the similar shape of the raw spectrum in 3 different runs?
Yeah. Yeah, this is one. Okay, this particular one is just this whole set is one of the run. If you look at my paper on archive, that's previous run. So we have exact same spectrum. This has been done like 2 weeks ago. Yeah, this is very new result. Oh, well. We were just trying to understand, will HD metallize before H2 or D2? How this 0 point energy going to affect, what's the order? Let's say H2 metallized at 500, D2 will be lower or higher because of the 0 point energy, but D2, hydrogen has highest 0 point energy, so probably hydrogen metallized before. So we were interested in if you add HD, if you have HD, well, what will happen? Will it metallize at lower pressures? That was the main thing. We were not expecting to see this dissociation. And also we were interested, in a way we were interested because at lower pressures we saw this one, H2, when you put H2 and D2, it make HD. But the other transition, HD going to H2 and D2 was not observed up to 160 GPa. So in one sense, we want to know how stable is HD under pressure, pure HD, and also in terms of metallization, will it be lower than the other material? But then now we have clusters. You have H2, D2, and HD. So I don't know how that's going to play in terms of metallization. But one thing we conclude is, one significant thing is conclude is not stable above 200 GPa. Yes.
You also said that the 381 is very dark.
Yes, exactly. This is, transmittance. This is transmittance. Thank you. Yeah, what you are seeing, so this is, what you're seeing is the transmitted intensity. Oh, these are just stacked. Oh, yeah. So what you're saying is this value. Yeah. Okay. That's different. I'll just stack them on a plot. You can't get a qualitative value. I mean, this doesn't represent anything right here. I don't have any scale right here. So if you take individually spectrum, it's different intensity.
Right. So you're
Yeah, I just stack them.
intensity.
Yeah, I just stack them together. That's why if you look at it, this plot, it's not same. I enhance this.
What I'm worried about is if you're 381, like what would it look like if there was no hydrogen there at all?
So if you look at right here, so these are on the same scale right now.
Yeah, I don't want to look at these. I want to look at your actual measurements. So you go back.
This is coming from actual measurement.
Yeah, I understand it's after you treat it. So I want to go back to the actual thing. So here, I mean, your 381 curve, what would it look like if there was no hydrogen there at all?
So nothing at all. It's like empty. Yeah, empty. So you will not see this. So
Black curve.
you will see some bump. There's no any transmit. There's no any absorption right here, and also you will not see anything else. So it's going to be here. You have phase 3, right?
No, I'm asking about the black one.
Okay. To answer that one, I have to use this one. So here you don't have anything. But if you go up here, what you're going to see is something very flat line, just like this. Here you have something that you don't have anything, right? If you go without hydrogen, you will see nothing here or anything.
Well, I mean, the diamond is getting dark too. So, well, but I guess it would be
Well, yeah, we're talking about here is 3,000. This is 3,000 inverse centimeter.
Right,
Which diamond are you thinking of?
well, the one that you used, I mean, it would be interesting to see if the diamond,
Oh, it's the empty diamond. If you
spectrum.
don't have any empty diamond, this is how it's going to look. Like this.
It's actually third order form of spectrum. As far as
Oh.
I remember. This down-looking kind of structure is from
Right,
columns.
see, yeah, this is what I'm talking about. So no sample there. It would be interesting to see that. Okay, so that's a 360.
It's high order form of
No sample is ambient pressure.
Yeah. Yeah, but your D is different. So, but if you use the same pressure at higher temperature, your thickness is similar. So you will get a more qualitative value.
Oh, no, so your no sample is not measured at 360.
Yeah, yeah. Of course, this is this. Here, this is the same pressure.
Yeah, I would be interested in seeing like a controlled sample that measures hydrogen.
Yeah, it'll be like very similar to this blue one, and except this peak.
So I have a question about your
Yes.
So you're measuring
Yes. Yeah. Yes.
plasma frequency 33 and your highest energy.
Yeah. I mean,
Comment on the range of statistically acceptable
yeah. That's true. Yeah.
values for plasma frequency.
Yeah.
Stocks with this
It's a very good question. Yeah. I mean, yeah. I mean, we get like around 3.5 plus minus error for these plasma frequencies. It's huge, and I understand that. Like, it's in terms of statistically, it's a huge error right here. We need a better model or better understanding how diamond absorption works right here. 3.5. 3.5. So this is coming from your fitting, your standard deviation from your fit here. Yeah, okay. Yeah, I understand that it's a huge error here. So that's why we were trying to come up with a better model to understand this one with the diamond absorption, and we're trying to now do the separate experiment how the diamonds just absorb, and use that one so that we can really use this 4-point. And also we're trying to get more energy, the more points right here. To
Why are you ignoring your
yeah, it's because of the absorption. These are affected by the absorption. So diamond absorption, we don't know how accurate this well is. So Tim, I understand it. So what the best answer I can do is the more work coming to address this issue. Yeah, these are always reflected.
What does that mean?
It's just detect from the. We have a very standard technique. We shine the laser, get the normal incident, and we collect it. We have a detector, we have a chopper, and we collect it. So the values is coming from that. So diamond surface, the unstressed diamond table. Yes. Yeah. Yeah. So you get your diamond surface table and go in and back all wavelengths, whatever the wavelength you use. Yeah, you go back and forth. So we have different analysis coming too now. We're using the rhenium as your reference. It's maybe a much better, less error on that one. But if you use the rhenium itself, because now you can remove the diamond absorption part. So we haven't concluded those things. So yeah.
So when you say go back, what do you do?
Yes. Yeah. We have control. We can move the sample in and out. Sure. Yeah. Yes, yeah.
Judging from this work,
Yeah. It's, yeah.
diamond absorption is few orders of
Yep.
which does really fit in what
Yeah,
you
yeah.
showed.
Yeah, exactly.
Any comment on that?
Yes, yes. So to be one thing to point it out, there was an error term coming. We submitted error term because of this. We made an error in our calculation, so it's coming in on science. So the Vora's paper itself, it has some errors. We discussed with him. He was assuming that the metal that he was using doesn't change the reflect. He was using ambient conditions to reference his absorption to higher pressures too. And then his equation said those pressures were off, and there were some issues. And according to that paper, around even 200 GPa, it's really dark diamond. According to his OD values, like which we all know that it's not the case in our normal experiment. So that reference is to use in the first place is wrong. So we made a mistake using that and all our calculations. So we corrected that one and submitted. Yeah. 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 So we corrected that. Yeah, we corrected that one. And then we have more new experiment coming on. We're doing on diamond absorption in our conditions, our same diamond, same configuration, and study the absorption. So then we can correct this one according to that. And also, yeah, more data. Yeah.
So is also all the pressure you're showing here is
In this one or my the diamond vibron, we use the diamond vibron for the raw spectrum. I was showing you the IR up to 400 GPa. That I use diamond. But this one, in this run, only the highest pressure point, only this one being used. I use diamond line to measure pressure for only this pressure point. And the low pressure points, I was using the IR vibron, which is calibrated by others, to measure the pressure, up to 360 GPa. So 360 GPa to 495 GPa. In this run, the shiny sample run, we did not measure the pressure directly, but we measure the pressure at this point by using the diamond. So in between, there's 360 to 495, there's no any pressure measurement. But we calibrate our strain gauge, our the load versus pressure. So we were using that to extrapolate that one, but at the higher pressure point, we did measure using diamond. This is measured value, but right here, this one was not measured. It's from the extrapolation for load versus pressure. And 200 GPa, this is measured by using diamond vibron done by Ja and others. But these ones, run 3 here, third run, we were using the diamond H2 vibron as well and diamond. So we were using both of them right here. So not just vibron. We were tracking the diamond line from lower pressures to all the way to 380 GPa right here. Sure. transport measurement?
Transmission.
Oh. You mean this? This one?
Just images.
Oh, just images. Yeah. These are all the images I have right here. Oh, you mean this one? Yes.
So here you see the going at high pressure diameter becomes kind of darker. So this transmission, could you separate what comes?
Do you have any OD for this? Is that what? No, I don't. But what we are planning on doing is, we have really put a sample right here. Yeah, yeah. Say it again. I don't think so. We are at 5 Kelvin, and when you go to really high pressure, I don't think it's really matters orthopara.
So when you get another shiny,
Yeah, sure.
what measurements
Oh, yeah.
make to try to convince?
So our next measurement is we were not thinking of doing optical measurement this time, so we want to put the electrodes. So we are developing a new technique to, doing conductivity to that pressure is tricky. We can do 200, 300 GPa easily, but more than that, you have to have something new. So there is some new development. Seems promising, so yeah, we have to wait and see. So that's next project, and whatever the ongoing thing right now happening.
What if you can't do that, but you can get another cell in the
So
optical measurement?
yeah, optical measurement we can always track. So while we were even doing conductivity measurement, we can do the optical measurement, right? So it's not that we are not going to completely abandon that. We're going to track that too. So in terms of optical measurement, what we were thinking is we need a broadband. So do the broadband reflectivity and really understand how the diamond absorption works. So and AL203, how that undergo changes under pressure, just studying pure AL203. So those are the new things think of adding in terms of doing conductivity measurements.
So I'm curious, so when you get to the shiny example, what happens? Trying to increase more pressure break?
No, while we were increasing, we were tracking how it changes, and we were trying to get the IR, but no signal, and then we saw all those things we were tracking. Then it got started to be reflective around 460 GPa. Then it got really reflective around 495. So after that, we stopped. We didn't increase. Then we did all these optical measurements, get the reflectivity and all this pressure and everything. And then we tried to measure the pressure again. We shined the laser, and that popped the diamond. Yeah. We don't have a broadband. It's just a one laser. We're using, like, let's say red. 532, shine the 532, and collect the spectrum. And shine the 1550 nanometer, collect it. Yeah, that's what, we need to do that, yes. For the pressure? I would say at least plus minus 30, 40 GPa. Go ahead, yeah.
Did you publish those pictures of tracking how shiny it looked with pressure?
This one?
You said at 460 it becomes somewhat shiny.
Oh, yeah. You mean this one, right? Yeah. So yeah, we have more pictures like tracking this one. I mean, we thought of picking only, what's important is transparent, opaque, and reflective. Yeah.
200 or 100 GPa.
Yeah. I have more pictures I can show you in all right. So yeah. Yeah, this the diamond absorption is a big issue. So we're trying to resolve that one. Hi, I'm Ranga. Nice to meet you. Hi. Oh, okay. So you working? එකතු වෙලා කරනවා. Oh, I see. Okay.